All right, let's pick up where we left off. So in this example, we want to know how long will it take for 90% of the hydrogen peroxide to decompose. So there's a couple of ways to do this. The first way is to go about saying, okay, if 90% has decomposed, that means 10% remains. So if we want to figure out A sub t, you can take 0.1 times your initial concentration, which is 0.30 molar, and find that at this point in time, 0.030 molar remains. But since we have the natural log of A sub t over A sub naught, it doesn't matter what the initial concentration was for this first order reaction. And this only works for a first order reaction. Since it says here that 90% decomposes, since there's only 10% that remains, we can go ahead and instead of writing the natural log of 0.030 molar over 0.30 molar like this, we could also just go through and write, well, since 10% remains, the natural log 0.10. Units will cancel out, so it should end up giving you that. So then from here, that will be equal to negative kT, so negative 1.8 times 10 to the negative fifth per second. We're trying to solve for time. So now you just have to plug and chug. We find that time is equal to 130,000 seconds, or approximately 36 hours. All right, so the other thing that we might be asked to calculate is the half-life. And you'll see this written as T sub half. So the half-life, by definition, is the time required for the reactant concentration to drop to 1/2 of its initial value. So here, we can write our integrated rate log in. So we have the ln of A sub t over A sub naught is equal to negative k t sub 1/2. And this, again, this only works for first order reactions. It doesn't matter what the initial concentration is, since you're taking the natural log of A sub t over A sub naught. If your initial concentration was 4, then by definition your half-life, the concentration would be 2. If your initial concentration was 2,000, then it would be 1,000. But all those simplify to the natural log of 1/2 is equal to negative kT sub half. So now we can, if we plug in the natural log of 1/2, we have the half-life is equal to 0.693 over k. So this is the one order. So first order is the one order of a reaction where we have this convenient equation for the half-life. You can't do this for all of the other orders of reactions. You'd have to plug in half of the concentration into them, but this does work out for first order reactions. So if we want to find the half-life here for our reaction that we've been looking at, which is the decomposition of hydrogen peroxide, what we would do is we can go ahead and plug in the half-life reaction, and there's a couple different ways you can do it. If you remember the half-life reaction, you can use that. You can say, well, T sub half is equal to 0.693 over K. Or if you're like me and you don't want to memorize that equation, you just put the natural log of 1 over 2. Okay, and that'll give you your half-life is equal to negative K times T. These are both equivalent. Just it depends on how you want to go through and solve it. And upon solving, what you should find is that your half-life here is equal to 39,000 seconds. So get a few more examples and we'll wrap up our integrated rate laws for the first order reactions. Anytime you see something that has to do with kinetics and radiochemistry. So if you see nuclear chemistry, something about a radioisotope, they always have first order kinetics. So we can use the integrated rate law for a first order reaction. So here it says the decay constant for sodium-24, a radioisotope used medically in blood studies, is 4.63 times 10 to the negative second per hour. What is the half-life of sodium-24? So what we can do, you can use your half-life equation. T sub half is equal to 0.693 divided by K, 4.63 times 10 to the negative second per hour. And then, let's see, T sub half should then end up being 15.0 hours. Okay? Let's do a couple more examples. So here, the half-life of radon-222, a radioactive gas of concern, is 3.82 days. What is the decay constant? So instead of looking for T sub half is equal to 0.693 over K, we have to solve for K, so cross multiply divide. So now we have K is equal to 0.693 divided by the half-life, which in this case is 3.82 days. And then we find here that K is 1.81 times 10 to the negative first per day. Now, the next type of problem tends to be more common, and it looks a little more complicated, but there's just one extra step added. So if we read this problem, it says phosphorus 32 has a half-life of 14.26 days. What percent of a sample remains after 35 days? So what we need to do is we need to break this problem down into two parts. Since it tells us the half-life is 14.26 days, we can use our half-life equation to find K. We have to know the rate constant in order to solve for what percent of our sample remains. So we'll take K is equal to 0.693, and then for sig figs, if you take the natural log 1 over 2, it's 0.6931 over the half-life, so 14.26 days. You find your rate constant to be 4.860 times 10 to the negative second per day. Then from here, since it asks what percent of a sample remains, it doesn't matter what your initial concentration is for a first order reaction, because it's A sub T over A sub naught, where in this case it's the concentration of phosphorus 32. So now what we can do is we can plug in to our integrated rate law. So natural log of A sub T over A sub naught is equal to negative 4.860 times 10 to the negative second per day times our time, which is 35.0 days. Days cancel out. And we end up with the natural log of A sub T over A sub naught equaling something. 0. Actually, let's just go ahead and get rid of this natural log here. We'll take the natural log of both sides. What we should end up finding is that A sub T over A naught is equal to 0.183. But since it asks for what percent remains, we're going to have to multiply by 100%. So what we would say is that 18.3% remains. All right, so to review on this problem, what we had to do is we were given a half-life and we want to know what percent remains after 35 days. Well, if we want to know how much remains, what that means is we have to find the rate constant K. So we are able to use the half-life, use this equation right here, rearrange and solve for K. And then once we found this rate constant, we were able to substitute it in down here. Okay, we could substitute right into our integrated rate law, so the natural log of AT over A sub naught. And then to solve for this fraction, or the ratio of A sub t over A naught, how much remains, you had to get rid of the natural log. And then from there you were able to find the fraction of A sub t over A sub naught. We found it was 0.183, so then you had to multiply by 18.3, or you multiply by 100 to get 18.3% remains. If it asks you how much was consumed, then you would just take 100 minus the 18.3 to tell how much is consumed. All right, so that does it for our integrated rate laws for first order reactions. Next time we'll pick it up with integrated rate laws for second order reactions.